So functional coverage has been three-part series. In the series one, we looked at cover group as a whole, and then we understood like overall for building a coverage solution, we need to declare the cover group and we need to create a handle, and then we need to instances using it new, and then either attach an implicit or explicit sampling. And then in the part 2 we decided to dissect into the cover group, and within the cover group again there are three elements. We have options, cover point and its bin management, cross and its bins management. So in the series 2 we were able to complete looking into the cover point and how to use various operators to manage the bins, the value range transition bins for the cover point. As a part of this final series 3, we will dig deeper into how to create crosses, and then main important concept of how to manage the bins for the crosses. That's the key concept. And followed by that we'll look into the options that are supported, which are going to be like a cover group as a whole and for the per instance of the cover group. And then we'll close it with the coverage methods that are supported. So let's dig into the part 3. We have looked so far in detail into the cover point and how to create different type of bins for the cover point, be it values, value ranges, transitions, legal bins, ignore bins, illegal bins. So we have looked at those aspects. So let's look at the cross now. Cross is built on the top of cover points, and what happens is in any given design you have always multiple variables. So it can be like you have different configurations, and within each configuration you can have multiple features, right? So now what you need to do is in all possible configurations you need to exercise that particular feature. So as simple as like let's say you have a mask bit and you have an interrupt. So interrupt can be masked, right? So now you want to generate interrupt when the mask is enabled, and you want to generate the interrupt when mask is disabled. To verify the behavior correctly, you need both the types of stimuluses, right? That's at a very simple level. Or you can have different type of operands, right? So the operands could be like a register operand, memory operand, and then you have different type of operations. Now with each operation you need to exercise all different types of operands. So in those type of scenarios wherein you require to cover not only just the values of the certain variables independently, but you need to cover them together in combination, right? So it's not just sufficient to cover operations, and it's not just sufficient to cover the operands independently, saying that we have seen register operand and then the memory operands, but those register and memory operands have to be seen with all the types of operation type of instructions, right? And we have seen, for example, memory, we had looked at addresses, and we have to do the read and write both the types of accesses to those type of addresses. So in this way, when you have a requirement wherein it's not sufficient just to cover particular values independently, when they need to be covered in combination, is when you use the cross, and cross is typically built on the top of the cover points. So for the individual values you define cover points, and whichever have relationships then you combine them together and cover them in combination using the cross construct. So let's just quickly, I know we have looked at it, let's just quickly define the cross problem a little bit as to how does a cross behave. So let's say I have cover point on A, B, C. Then each one of them, let's say, are they contain two bins, that is A, B, C are bit type of data, so it will result in two unique values. So if I concat, because if I want to cover them in combination, so in the absence of cross, what I would do? See, we should always think like this. In the absence of a particular construct, is there an existing thing that I can use to implement it? It gives us a clarity. It gives us the clarity in terms of the fundamentally what that particular construct is going to do. We don't have to go the entire length of re-implementing everything, but in the absence, how would we do it? Using the existing constructs that we have understood gives us the path to go from something that we know to something that we don't know, right? So it gives us a path to go from known to unknown. So here we know the cover point construct, we know we can concat value. So what we do is we will concat these three variables, and which will result in 3 bits, and then I can cover these 3-bit variable, right? I can still put a cover point on this concatenated expression, and then I will get unique values, and those unique values is nothing but a cross. Okay, so the same cross I can create by using the cross construct as well. So here what I'm doing is we have defined the cover point for each one of these particular variables that we have, and then we are saying this is the cross equivalent, wherein we are putting the cover point and we are concatenating the 3 values and covering it, and if I want to use the built-in construct, then I can just say ABC cross. Similar to cover point, you can give a name to the cross, colon, and again re-emphasizing you should give the names, because you are ultimately writing coverage not to ease the way of writing coverage. So if I don't give the name, of course it's optional, it's not going to give me an error, and maybe it saves me a few minutes of time of typing that particular variable name, but eventually while you do the analysis of coverage report, it becomes very hard. So you should always write coverage such that even if it takes longer to write, it is fine, but your analysis should become easy, because you are going to repeatedly do the functional coverage analysis. Functional coverage analysis is not like you do it one day and it's done. Okay, so you run certain set of tests, you get some coverage reports, you look at it, you understand what is not covered, again you do some changes to test benches, you add new tests, again you rerun the regression and look at the coverage. So it's an iterative process. So if you ease the coverage writing such that, if you do the coverage writing such that your coverage report analysis becomes simpler, that serves you longer, right? That few minutes that you saved while writing the code is not worth it. So you have to put some effort to define the right names for the cover points, right name for the bins, right level of grouping of bins, giving the names to crosses. All these are not just aesthetic, but they are going to help you while you do the coverage report analysis. So you better invest that time in it. So we will give a name saying ABC cross equivalent colon, and then we have set this cover point, and the same thing we can represent it using the cross construct by saying ABC cross, and I give the colon and I use the cross keyword, and then in the comma separated way I will provide the variable names. Okay, so here there are 2 ways in which you can define crosses. You can use the variables themselves directly over here, that is also as a legally allowed syntax, and what the cross will do is it will create an implicit cover points for the variables that you have defined, and then for those cover points it will also create auto bins, right? Those auto bin max variable that we have looked at, those many number of bins will be maximally created, and it can create a cross. Or you can directly use this cover points that you have named. So if you have named and if you have given the labels to the cover point, the same names can be used for creating cross. So here I could be writing A underscore CP, B underscore CP, and C underscore CP. Okay, so now a question might come in your mind that why do I really need to do this, right? Why do I, like, how do I choose between using the variables directly versus the using the cover points for those particular variables? So that's a question that might come in your mind. So what you need to think about it is that this implicit cover point also creates implicit bins. Okay, so there you don't have control on the way you name the bins. Okay, so but if you define explicit cover points that you intend to use in cross, you can still define the bin names. Right here I have not defined because it is very simple, but you can define the bin names, and then defining those bin names ensures that those bin names appear when we look at the coverage report for a cross. That is very useful, as we talked about, right? So that's why it's recommended that you explicitly define cover points and use those cover points for defining the cross instead of directly using the variables to define the cross. Okay, so that's one thing that you want to keep in mind. And then whenever you define the cross, the bins will get automatically created, and they will use this naming called auto n. Okay, we will look into it a little bit detail as we go further. And then with the crosses, the total number of bins will grow exponentially, right? Here itself, if you can see, with these three, it has become 8 already. So individual cover points had only 2, but with 3 cover points put together, it has become 8. So this way, when you cross multiple variables together, the total number of variables, the total number of bins that created in the cross can grow very quickly. So what you need is you need a way to manage them, right? So typical way we go about managing bins for a cross is that for the most part you rely on the auto generated bins, and then what you do is the name few of the bins if you really care for it, but most of the time you tend to create ignore bins. Okay, so we will look at this. So you let everything be created and then you exclude pockets of it instead of including. So when you define cover point, our strategy is inclusion, and by defining explicit bins, because there are fewer values. But when you create cross, the total number of state space explodes. So now you focus on excluding pockets of invalid bins and rely on automatically generated bins. So that is the general strategy that is used with respect to bin management. And we will look at the operators as well. How do they help us implement this strategy in the next few slides? Let's look at one more use case for the cross, and then we'll go into the details of how to define various bins and how to manage them. We'll look into those details. So UART design, for example, okay, it supports, so as we know, it is capable of serially transmitting and receiving the data, and you can configure like the word length, that's how many bits do you want to program once in a parallel format that gets converted serially and transmitted. Then you have the programmability to control whether the stop bit that's sent at the end, does it need to be enabled or disabled. And then you have the parity, different types of parity, so you can select the type of parity that you want, or no parity, so you can do that. Now what happens is this is all changes the way data gets transmitted on the line, and then the UART needs to be exercised in all possible combination of these programmable parameters. So for this type of a scenario, cross is very helpful in making sure that we have transmitted and received the data in all possible configurations, right? So that is when we can say it's really operational. So how do you do it? Like, let's say we define this word length, and then we look at that particular register where we control the word length that is configured in the design, and then we specify the bins to capture it, and then the stop bit enable and disable is captured, and then you have the parity, right? So like if it is a no parity, even parity, odd parity, and then bunch of other parity options, right? So you look at which is the parity that is programmed, and then you cross all of them, right? Like the word length, stop bit, parity. I'm showing fewer programmable parameters. There can be more such programmable parameters. So for all key programmable parameters, you want to cross them and make sure that in all possible combinations we have been able to one is that we have programmed the UART, right? And then second is in that particular configuration we have really done the transmission and reception of data. Both have to be checked. So here we are just checking whether we have programmed all possible configurations in the UART. This is just one part of it. Additionally, we need to make sure that in this particular configuration the actual data transmission has taken place, because without the data transmission, right, just programming something in the design is useless, correct? We have to actually exercise it, and you program it and then you utilize that particular configuration. So then we can say that yeah, this is really exercised. But this gives you an idea that how crosses can be utilized. So as we saw, defining a cross is a very simple process. You just give a label, use the keyword cross, and then you provide the set of the cover point names in a comma separated form that you want to cross. But the main challenge with respect to cross is the total number of bins that get created. It's easy to define a cross, but it's very hard to close the coverage on the cross that you have created. And the way you tackle that particular problem is that you define the user defined bins, which either merge these multiple bins to a single bin, or you eliminate some bins that are not relevant. Okay, that is what you need to do, because what happens is, like as we saw in our previous example, we had those three single bit variables being covered, each one of them giving rise to two values, so 8 bins. As soon as I cross those three variables, right, I immediately got 8 bins. So 8 unique, per unique combination of the cross you get one bin. Okay, so imagine that if instead of one bit, if those were 8 bins, if instead of containing two bins, if they contained 8 bins, that is if they were just a 3-bit variable, right, then, and if they contained 8 combinations, so immediately you have 512 bins, right? 8 8s are 64, 64 8s are 512, so you have 512 bins that you need to address. So it so quickly expands. And one way that in the cover point we could control the number of automatically created bins was using the auto bin max, but there is nothing such that in the cross. Okay, there is a similar option that used to exist to control the number of bins in the cross in the older versions of LRM, but due to some confusions, the auto bin max for a cross type of an option has been removed from the latest LRM. So you don't have an option to, like what I'm saying is, there's no LRM defined option to control the total number of automatic bins. It's only dependent upon the number of bins that are already present in the cover point. And the point to note is, like in the case of cover point, what used to happen was, once we define a user defined bins, then it used to disable the auto bin generation. It will, once in a cover point, if you create few user defined bins, only those bins will be considered. The automatic binning will be automatically disabled, right? Whereas in case of cross, what happens is, even if you have user defined bins, if you have user defined legal bins I'm talking about, then those will coexist with the automatically generated bins. Okay, so the user defined bins, what they will do is, they will eliminate the cross bins on which they already are intersecting. Okay, so if I have created those 8 combinations, and among them I am saying, okay, the 2 combinations together I am defining it as one bin, then out of those 8, 2 gets eliminated, but the 6 will still remain. So I will have this one bin in the cross that covers 2 values, and I will still have those additional 4 bins, right? Those will still not the additional 6 bins that will still continue to exist, and the total bins that we are still covering is 8. So that way, creating legal bins in the cross doesn't eliminate the other bins. Whereas if you had done the same in the cover point, if I defined few bins, then the remaining values will not be tracked, but that doesn't happen with the cross. Okay, and when you use the, so this is a point we have already emphasized, but just will call it out in this context of auto binning. So if you, instead of using the cover point for creating crosses, if you directly use the variables, right, then what will happen is, those variables, unless the auto bin max is changed, will have maximum 64 bin spread, right? That gets automatically created. And as we discussed, it's generally a good idea to not to do this and focus, because a good cover point in leads to a good cross coverage bins. So because if you have taken care to define the bins correctly for a cover point, then your cross bins will also, the managing them will become easy. If you don't take care, and if you bring in the raw crosses to raw cover points to do the cross, then the overall bin explosion becomes even higher. So this is a way that this is how we kind of compare the this is how we compare the cover point and the cross bins. And what we need to take it away are, the takeaway from this particular discussion is that they are not same, they are very different. So this is something that you need to keep in mind. And so let's look into it further, a little bit further, to understand now how to use some of the operators that are provided with the cross bin construction to either merge them or eliminate them. So let's look at that in the next few slides. We will look at certain operators, the operators in the cross bin management that help us either group multiple bins together for either the selection to create a single bin, or to elimination through the ignore bins, right? So that is what we really want to do. So the way we will go about it is, we'll look at few operators that are provided in which help us to accomplish that, and then we'll look at some of the examples to see how they are used. So that's what we will do it in the next few slides. So these are slightly tricky, so I would like you guys to pay attention. When we created cover point, right? So cover point bins were values. Okay, they were, although we defined it as range in some cases, but still they were the individual values, right? So you remember, like a single number versus a complex number, right? So in the mathematics, a complex number always had two components, right? So like that, cross bins are tuples. Okay, so they contain multiple values, because minimum you need two cover points to create a cross. So if you create a cross even using two cover points, then each bin in that gets created in that particular cross will have two values. Okay, so that's why it's called as tuples. But I'm not saying it's limited to two values, but it is basically more than one value. That's what the point I'm trying to make. So if you cross as many cover points, then each bin that gets created in the cross will have so many values from each of those cover points, right? So that's what happens when you cross them together, and then each tuple contains a unique values from the cover point that you have crossed. So that is the base way in which the bins get created for the cross. Now we look at few operators. So you have an operator called bins of. Okay, so the bins of, what it does is it yields bins of its expression. Okay, and this can be either a cover point or a cover point bin. Okay, you can for the bins of operator, you can either pass a cover point name. If you pass a cover point name, then it provides all the bins that are present in that particular cover point. Or you can pass a bin name, and it gives you all the values that are present in that particular bin. Okay, so if I pass a cover point name, then the values of all the bins, right, that gets returned. But if I pass a bin, then all the values that are represented by that particular bin will be returned by the bins of operator. And we'll look at the example. So first step in the either grouping or elimination is, you need to have ability to get the bins from the cover point that you are crossing. So that you accomplish with the help of bins of. And then next you use, there is another operator called intersect. So what you do is, the resulting bins from the bins of, you do the further selection, which can be either inclusion or exclusion, with some values which you define using the intersect. Okay, so you have gotten set of values. When you set bins of a particular cover point or a bin, you got certain set of values. Okay, now what you want to do, you want to either select some values from that, or you want to remove some values from that, and that you can accomplish using the intersect. So you can say these values intersecting with another set of values now gives you the control that you get the ability to pick only a subset of values from that. If you want negation, of course you can negate it, right? Use the negation operator and you can negate it. So then if I eliminate, like if I have a big range and if I eliminate a subset, then the remaining values I can utilize. So one of the ways, then you can build the selection. Okay, and then so this combinations of bins of and the intersect operator together, multiple of them can be combined, because what you are doing is, when you are building a cross, you are creating cross using multiple cover points. So what you would like to do, you would like to pick and choose certain set of bin values from different cover points, right? So what you can do is, you can say bins of a cover point 1 intersecting with certain values, and then you can either use the logical operator and, or a logical operator or, to combine that with the values from the other cover points as well. Okay, so I can say bins of cover point 1 intersecting with certain set of values, or bins of cover point 2 intersecting with certain other set of values. So I want only the cross bins that contain these subset of values from these cover points. If these particular values are not present, then I do not want them to be, you can either ignore them, or you can group them in a certain other ways. So you can manage them. Got it, right? So this is the way it provides you to way to select it. So once you have selected it, either you can group them and make it a single bin, or use ignore bins to eliminate them. So that is the first level. Okay, so the first level is you have this selection operator, which you call it as bins of and intersect, that allows you to define the subset of values, and those can be again combined with the logical operators to further filter it across all the cover points that you have crossed. The second thing is there is another operator called with. Okay, so now with, what you can do is you can specify an additional condition on the top of either the selection criteria or independently. Okay, so you can use, like for example, a cover point identifier with, and then provide a condition that selects the values. Okay, so when you look at the example, it will become more clear. So, or you can use with a particular cross identifier and then define the selection criteria that selects the set of tuples. So now with can be either used independently on a particular cover point, or it can be used directly on a cross, or it can be used on one of the selection criteria. Okay, so any set of bins, however you have gotten it, either directly from a cover point or directly from a cross or from a selection criteria which is based on bins of and intersect, you can specify an additional qualifying condition, and then again say that okay, if this particular condition is met, then only select those set of bins. So that is what with allows. So with kind of iterates over all the values of that you have provided and checks a certain condition that you are providing, and if that condition is true, then only it selects those values. So that's what the with will do for you. Along with this, the third operator is an optional operator called matches, and what it does is it represents a selection policy where there should be some number of minimum number of satisfying values of tuples. This is only applicable for cross bins. Tuples required to select a candidate bin tuple. So what happens is either I could be using a selection criteria and I can use it with matches, or I can use with and then matches, or I can do bins of, filter it using with and then go to matches. So what it is trying to control is how many number of values should be matching, okay, in order for me to define a particular bin. Okay, so that is what it will control. If unless and until it is so many number of bins that are so many number of values, actually value tuples that are matching, then you don't create a bin. Only you create a bin if it is matching so many tuples. Okay, so that is something that you can do. I think it will become more clear when you look at an example, but we still need to define it formally before we jump into example. So when you omit the match, then the default selection policy is that even if there is one matching value, then that particular bin gets created. Okay, but when you use matches, then from your selection criteria, you need to have certain number of matching values in order for that particular bin, that whatever you are defining, to get created. Okay, so that is the that's the point behind the matches. So let's now jump into some examples to see these in action. Okay, we have looked at operators to select set of bins. So we will look at some of the examples. So in this example, we'll look at how to merge multiple bins into a single bin, and how does the selection operators helps us to do that, and how do they behave. So we'll probe deeper and understand that. So in this example, what we have is we have two 8-bit bit vectors, and one of them is called v underscore a and another is called v underscore b. We have defined two cover points, cover point a for the value v underscore a and cover point b for the vector v underscore b, and both of these are visible to this cover group because of the scope, and this cover group is using the implicit sampling. And what we have done is we have crossed these two cover points, this is a and b, we have crossed it to define another cover point C, and what we are interested in is these three bins and what values are they getting. That's what we are interested in. So let's jump into the first bin, which is C1, and what we are saying over here is not of bins of A. So we had already looked at the operator bins of A. or the bins of operator. So bins of, what it does is it provides you all the bins of either a cover point or a bin that you have specified. So here we have specified a cover point. So once we have specified cover point A, if you look at it, the cover point A has these 4 bins, which is A1, A2, A3 and A4. All 4 of them are arranged bins, so we will be able to get all 4 of them. And then what we are doing, we are using the intersect. Okay, with the intersect we are specifying set of values to select certain set of bins from this list. Okay, so what happens? So we are saying intersect 100 to 200. Okay, so now if we come back to these bins, if you see this particular values 100 to 200 doesn't have any intersect with the bin A1 because it's only from 0 to 63. Whereas with A2, yeah, we have some intersect from 100 to 127, we have the intersect. And then with bin A3 also we have the intersect, right? So that is 128 to 191 is in this range. So we have the intersect. Look at bin A4, which is from 192. So 192 to 200. Okay, so that also is intersecting. So it is intersecting with all these 3 bins. Okay, so what it means now is that, and we are saying not. If we didn't have this not, then what would have happened is we would have selected bins A2, A3, A4 from the list. Because now we are using the negation, it will lead to only selection of the bin A1. Now what does that mean? So what it means is we have to again remember the context that we are talking about is we are telling the cross bin selection criteria. Okay, so now and as we know, all the cross bins are tuples, and the tuples are created with the combinations of bins that we have defined over here. So if we didn't define any of these bins, then totally we would have had a 16 bins, right? Which would be containing these tuples A1, B1, A1, B2, A1, B3, A1, B4, so on and so forth up to A4, B1, A4, B2, A4, B3 and A4, B4. Okay, so we would have had these tuples present over here. Now what will happen is some of these tuples will get eliminated, and eliminated in the sense they will be grouped together as a single bin. So now C1 will contain these particular bins. Okay, so since C1 will now, because when we do this not, we are going to have only A1, so it will select the tuples where there is only A1 is present. So A1 is present in this first 4 bins, right? So we have A1, B1, A1, B2, A1, B3 and A1, B4. So now C1 will select only those 4 bins where the bin A1 is present. Okay, so that will be the C1. And when any of these 4 combination takes place, the bin count for C1 will be incremented. That is the first point. And second point is that these 4 bins will be eliminated from the auto generated bins. So okay, from the 16 now we have eliminated these 4 bins. So 4 bins are gone. Okay, so now we will be left with only 12 auto generated bins plus 1 bin C1 at this point of time. Okay, so that is what happens. Now let's take a look at the second one. So as we had discussed, to the bins of, we can either pass a cover point or we can pass a bin. So here we are passing the bin, which is bins of A dot A2, which means all the values that belong to the bin A2 will be listed over here. And then we had talked about, if you remember, we can combine the bins of operator with the logical or logical AND operator. So here we are using the logical OR, and we are saying bins of B dot B2. Okay, so we are saying all the values of B2. So now what will happen? All the tuples of the cross that have been auto generated, which have the bin value of either A2 or B2 will be used, and they will be grouped together as a single bin named C2. So what are those values? So those values will be these 7 cross products. Those will be A2B1, A2B2, A2B3 and then A2B4, right? And then it will have the places where B2 is present, right? So here we have B2. So in this first 4 that we discussed, there is A2 that is present. In the next ones, we are going to look at where the B2 is present. So we have A1 B2 and then A3 B2 and A4 B2. Okay, and if you are wondering, so with A2 we got 4, with B2 we are getting only 3, because A2 B2 is already included, correct? So that's why we will have 7 tuples that get included as the part of bins C2. Okay, so the C2, whenever any of these combination takes place, this particular bin will increment. Okay, and then these bins will be eliminated from the auto generated bins. Okay, and then only the rest of them which do not have the overlap will be retained. Okay, let's look at, so this is the way OR behaves. OR is behaving that either of them, when they are present, it is selecting those particular tuple values from the auto generated cross bins. Now let's look at the bin C3. So here we are saying bins of A.A1 and bins of B.B4. So which of the tuples among which we have the bin value A1 and bin value B4. So those will be only one. So that is, whenever you have A1 and B4, then only the bin C3 will be hit. So the bin C3 is nothing but now a very specific bin. So if you want a very specific bin, you can use this type of logical ANDing and define a very specific bin name for a particular value tuple. So that is possible. So now this bin also gets named, and it becomes the part of cross. So this 1 plus 7 and plus this 4, right, 12 of them become now the user defined bins, and remaining 4 will continue to remain as the auto generated bins. So that is how this particular cross will work. In the previous example, we had seen the bin selection operators, bins of, and then the intersect. So how do they operate? But we have two more bins selection operators, and those are with and matches. Okay, so we have already used with operator with the cover point, but we have not used it with the cross. So let's look at an example. How does it behave with a cross in this particular slide. So let's jump into this particular example. So in this example, what we have is we have two 8-bit vectors A and B, then we have one 8-bit parameter mask, and this mask should ideally be initialized with some legal 8-bit value for this cover group to work. Then we have cover group CG. It has two cover points A and B. Then the cover point A has two bins, low and high. Low is a bin per value. It's taking values from 0 to 127, which is 128, which will lead to creation of 128 bins. And whenever the corresponding value is sampled, then the corresponding bin will be incremented. So if the corresponding bin value is 127, then low of 127 will be incremented. Then high is representing a range from 128 to 255. This is again 128 values. When any one of the values happens in this particular range, the bin high will be incremented. Okay, then we have cover point B. This guy also has two bins. Both of them are value per bin, and then we have one mod 2 bin over here. And if you look at the usage, we are saying B with, so it operates as an iterator, and it will take go through all the values that the B can take. So in this case, B is a 8-bit vector, so it can take up to 255. So it will go through 0 to 255 values, and it will apply this particular expression item mod 2 equal to 0. Item, the name that we have used can be any name. We have just used item by default. That's what the LRM uses. So we have used item mod 2, but it could be I mod 2 as well. So you can use any variable name. So we are saying, so when it goes through each one of the values, if on that particular value, if this expression is satisfied, it is returned and it becomes a part of the bin. So what will happen? So 0, when it checks, yeah, so 0 mod 2 will be equal to 0. So first bin will be 2 of 0, and then when it checks for the 1, of course this is not going to satisfy, 1 mod 2 is not going to satisfy. When it checks for 2, 2 mod 2 will be equal to 0, and the second value will be 2, and so on and so forth. So it will have 0, 2, 4, 6, 8, and so on. And the second bin in the cover point bin, cover point B is 3, and this is the mod 3. Same set of operations are repeated, and this guy will contain values like 0, 3, 6, 9, 12, so on and so forth. Now we are creating one cross. The name of the cross is capital X, and we are crossing these two variables A and B. Since we have the cover point that's already defined, it's going to consider them, And now the important detail that we really need to look at is the way we are defining these two bins. Okay, so let's say we forget these two bins for a moment, and if I had just defined cross A, B, then I would have had a 4 cross products. Okay, what are those 4 cross products? So we have these two bin values, right? Low and high, and 2 and 3, right? So it would have gotten combined, and we would have seen like a low 2 and a low 3, high 2 and high 3, right? So that's how it would have gotten created 4 cross products. But since we have bin per value, each of those cross product will mean multiple tuples. Okay, so one cross product the way we are showing, but it's multiple tuple. For example, high of 2 will be high of 2 of 0, then high of 2 of 2, and so on and so forth up to high of 2 126. So all those values will be included when I'm saying that one particular representation, right? When I'm saying high and 2 of 2 over here, right? So that means all these values. Okay. So now let's look at how we can use the with and the matches operator. So what we are saying is bins apple equal to x with. So when I say x with, what it does is it operates on all the tuples that are created for this particular cross x. That's why we have expanded it over here to show you what that means, right? So it will take each of these values and it will add a plus b. Okay, so in that one, like for example here, whatever the value of high, okay, and then 2 of 0, right? So the value that whatever the combination that it is creating, right? So what combination? Let's say here now we take value 128, right? So 128 and 2 of 0 will be 128 plus 0, right? And then it could be 129 plus 0, so on and so forth, right? All the values that this particular range can take, plus the each unique value that the twos bins can take, right? So for all of those values, it's going to iterate and check that if a plus b is less than 257. Okay, so what happens over here? So if we look at high, right, it has 128 to 255. Okay, so if I take the bins of 2, then it will be 0, 2, 4, 6 and 8, right? So first value, if I take 0, then if I add 0 to the minimum, it will be 128. If I add to 255, 255 plus 0, it is still 255, and that's less than 257. So all those bins, meaning all these 128 bins will get included. Okay, and then what we say, we say that it matches with 127. So matches with 127 means it's looking at least 127 matches must be there. So since we have 128 matches, so this particular value will get selected. So we will have high and 2 of 0 getting selected. Now we'll check for the next value. So if we take high and 2 of 2, so when I add 2, okay, so what happens? 255 plus 2 will become 257. So that value is gone. Okay, so now we cannot have 128, but if I add 256 plus 254 plus 2, then that will become 256, which is still less than 257, and hence high and 2 of 2 will also get selected. But if I go to 2 of 3, okay, so that will not get selected because now I have to come one more value down, right? So then at the point where it reaches the 254 itself, right? Sorry, the 253 itself, we will have to cut it off, right? At the 253 plus the 4, right? There itself we are exceeding that particular range, and hence we will not be able to match 127 values when we go to 2 of 4. Okay, so it ends at high and 2 of 2 itself. Okay, but if we look at high and 3 of 0, right, the same logic that worked for high and 2 of 0 will come into play again. Okay, but same thing if we look at high and 3 of 3, right, so that also we will not be able to match the 127 values over there. Okay, what will happen is that we have to, when we add 3, so 255 plus 3, that value is eliminated. Then we have to go to 254. So 254 plus 3, right, it becomes 257. So that also eliminated. So once that is eliminated, then we cannot achieve 127 matches. Okay, so that is why it will be restricted only to high and 3 of 0. So only these 3 bins will become part of the apple. Okay, so that is how width and the matches work. Now let's look at plum. So the plum has two components, right? So we are using the logical OR over here. So we are saying bins of b of 2, okay, and then we are saying with b greater than 12. So what it is going to do is it's going to select all the bin values from this particular bin 2, which contains all our 0, 2, 4, 6, 8 and so on and so forth, with the value of that particular bin greater than 12, right? So if it is greater than 12, then only it will get selected. So it will start the selection from the 14. Okay, so it will not include any of the bins up to 12. It will start the selection from 14. What it means is that in that tuple that gets formed, right, their value of the b element that gets used should be greater than 12. So if it contains 14, 16, 18 and so on and so forth, those particular bins will be included over here. Okay, or a of low. Okay, a of low. So we are going to go to a and then low, which will select these all 128 values, and then that will be, you will do a bitwise ANDing with the values of the b. Okay, so each value of b that we have, so which will be both of these included, then each value of b, and that will be again ANDed with the mask. Okay, so the mask value has to, we have to define that, and if that expression happens to be true, then those bins will also get included. Okay, those bins will be included as a part of the plum. So plum will have these multiple matching bins, and whenever any of those tuples take place, the bin count for plum will be incremented, and those bins will be removed from the automatically generated bins. Okay, so that is how the bin selection criteria for the cross works, in order for either merging multiple values into a single values. So we have not used ignore bins in this particular example, so we will look at it in the next example. So we had seen the concept of ignore bins and illegal bins in the context of cover point. The same is applicable even in the context of crosses as well. And whatever the cross bin selection operators that we have seen, like bins of, intersect or matches with, those can be applied along with ignore bins and illegal bins as well, because all of these are like, the bin definition constructs. So they can take a set of tuples and yeah, they can implement whatever the name that you specify. So let's look at an example. So we have cover group read access CG. We have two cover points. We have RW address, and we are covering this particular variable WE. We have two bins read and write values 0 and 1, and then we have address where we are covering four different addresses. We have 0, 4, 8 and 28, and we are defining a cross called reg access, which is a cross of RW and address. So we will look at usage of ignore bins and illegal bins. So we are defining one ignore bins. So ignore bins is defined with this keyword ignore bins and read only. So now we have to define a criteria to select a set of bin tuples that needs to be ignored. So once we define ignore bins, those will be eliminated from the automatic generated bins for tracking of the hit counts. So what we are saying over here is we are saying bins of address, okay, so which will give us these four values intersect with 4 and 8. Okay, so this 4 and 8 will be eliminated, so we will be still left with 0 and 28, and that we are combining with the logical and we are saying bins of RW, which will be this, we will get read and write, and we are saying intersecting with 1, and the value of 1 happens to represent write. So this particular read only bin, it will ignore, okay, any writes that take place to value 4 and 8. Okay, so it will exclude writes that taking place to 4 and 8. Now let's take a look at illegal bins. As we have discussed already, illegal bins should not be relied on as a mechanism to do the checking, and in this particular case we are covering with the intent to showcase how this construct can be utilized, as well as in case if you are really doing any redundant checks through cover group, you can use it. So we are illegal bins is a keyword, so we are saying illegal bins, we are giving a name of the bin, and we are saying bins of address. Again it gives us these 4 bins intersect with 28 8 hex 28, so it will intersect the status address. And then we are saying again we are using the logical and we are saying bins of RW, which is again going to give me these 2 bins, read and write, intersect with 1, which will give me the write. So what we are saying is that we need to eliminate any writes, not eliminate, we need to mark the writes to the address 28, because it's a status register. Typically status registers are read, so if at all we see a write to the status register, what we are saying is it's illegal, and if at all that happens, then a runtime error will be flagged. So this is the way you can set up ignore bins. You can define multiple set of ignore bins, and multiple set of illegal bins can be defined in the cross. Okay, so at the beginning of this particular session on cover group, we had seen that options forms one of the elements of the cover group construct. So we had cover group construct, and we had options, we had cover point bins, we had cross, and then the cross bins. So and then the cover group had a different other features wherein we could pass arguments to the cover group, and those arguments can be used either for sampling certain variables, or can be used for setting the values for the options, or can be used even in case of the definition for the bin values. And then we had also looked at, like for example, the sampling functions, implicit, explicit sampling, and then we had also looked at how the built-in function sample itself can be overloaded to pass the values that can be used in your cover points for sampling. So we had looked at all those. The only element of the cover group construct that we had not touched was this options. So we'll now look at how do these options work. So options, what they predominantly do is they control the behavior of your cover group, cover point and cross, such that it results, when you use it, it results in the different ways in which the coverage gets reported. Okay, from each of these elements, when you use different options, the way coverage reporting happens will be different. Okay, so we will understand that how that is different. We'll look at few examples of the coverage reports by setting some of these key options, and we'll see how those behave. So there are 2 types of options. We have something called type underscore option. So type underscore option is a keyword, and then we have option. Option is a keyword. So type underscore option specifies the option for cover group type as a whole. Okay, and option specifies the options for a specific instance of the cover group. Okay, so when we declare cover group, we have seen it loosely behaves in a way similar to class. It's not exactly class. Okay, don't get confused with that. We are not saying it's like an object and all that concept, right? It's not object oriented inheritance polymorph, not in that way, but to the extent that, like when we declare a class, it becomes a data type, right? And then you can use that data type to create multiple handles, and then you call the constructor to create an object. In from that perspective, cover group behaves similar to class. That's the only point over here to correlate to something that we already know of. Cover group, as we have seen, it has to be instantiated in order to be used, and there can be a cases where your design can have multiple ports, right? Multiple ports means multiple instances of same design. Okay, on your laptop you might have seen multiple USB ports. So for that, in the SoC that's being used within your laptop, there has to be a multiple instance of your USB host controller, or a USB host controller with a multiple port needs to be instance. So when that particular design gets verified, and per instance of the design, then you are going to create an instance of the cover group as well. Okay, so why I am telling this is a question might come in your mind that why do I need to create multiple instances of cover group? So when you have the design itself is like that, where you have multiple instances of certain logic operational, then you might have to create the multiple instances of the corresponding cover groups as well. Okay, and note that those cover groups could be again both black box or white box, because even when you have multiple instances within your test bench, you need to create parallel threads to handle each one of them. For each parallel hardware, you need a parallel threads in the test bench, and those threads again will have driver, monitor and everything. Okay, so along with them you also attach a coverage model, and when you attach the coverage model, you need to also create multiple instances of that particular cover group. That's what we are talking about over here. So the one more point that you need to keep in mind is, so when we do that, okay, so now what you have one cover group data type and you are creating multiple instances of it. So when you say type options, the type option applies to cover group as a data type. Okay, and then option is for each one of these instances. Okay, and keep in mind that if I set something in the type option, don't think that it will automatically reflect to the instance options. It's not like that. Okay, it's only with respect to how the coverage gets reported at that point it affects. So what happens is, when your coverage is reported, it will report the coverage. So you have options through which you can control whether you want the coverage to be reported at a per instance level breakup, or you just want the aggregated across all the instances to be reported for the entire cover group. Okay, so that is what you control using the type options and the option. So we will look into it more detail. So coverage report for the entire cover group as a type, it's controlled through this merge instance option, and then for every instance is controlled through this per instance option. So we'll look into the details of each one of these in the subsequent slide with some examples. So let's look at how the coverage number gets computed and then how these options play a role in it. So at the top, you will get a top level functional coverage report that will be weighted average of all the cover group results. So let's say I have three cover groups. I have cover group 1 result, cover group 2 result, cover group 3 results, and then for each of these cover groups you can assign weights. And then it will, so what the simulator will do is it will take that weight into consideration, weight into the coverage contribution provided by that particular cover group, plus the weight of the cover group 2 into the coverage contribution that is provided by this specific cover group, so on and so forth, divided by the total coverage that each of the cover group is providing. It is using that it comes up with the final functional coverage number. The idea of weight is that if certain cover group is more important than other, then it should get more say in the overall functional coverage. Okay, so what that means is, if a cover group with a higher weight is being covered less, it will pull down the overall functional coverage. That is the idea of using the weight. So if you have a cover group with a lower weight, then even if it is higher covered, it won't contribute significantly to the overall functional coverage, because we are doing the weighted average of all the results. So that's one point to keep in mind when we say the overall coverage report, how it gets reported. Now subsequent to that, what happens is the cover, how now we need to understand, like we need to keep going one level down. Now how does a cover group 1 result itself gets computed, right? So this gets computed based on the coverage results of each of the instances of that particular cover group. And how does a cover group instances coverage gets computed? It's based on the coverage that is provided by the cover points and the crosses. So whatever the cover point, each of the cover point and crosses are providing, that gets averaged, and you get the score at each of the cover group instance level, and the score of all the cover group instances gets averaged, and you get the result for the cover group as a type. Okay. So now what we need to understand is that now at the cover group type level, we have two ways of averaging. So one is that you could just do like a average, weighted average of this cover groups instances. Okay, per instance I can assign a weight. Like let's say I have multiple instance design, I can control the weight for a given instance. So again I can do a weighted average coverage computation across the cover group instances of a specific cover group. Okay, that is possible because every cover group instance has this option. So through that option I can control the weight of that particular instance. So that is one thing I can do, and I can again control the weights provided to cover points and crosses. For example, if I define a cover point that I am going to use it only for the crosses, what I can do is I can set the weight for that particular cover point as 0, so that it doesn't double contribute in the coverage computation. Okay, so that is possible. So that is one way the hierarchically coverage gets computed. But when it comes to at the overall cover group as a type, okay, when it comes to computing that, there are two options. One is it can be a weighted average, or all cover group instances being ORed together. Okay, being ORed together means, let's say I have 4 bins. Okay, let's say, to make it simple, let's say I have 3 bins, and each of the cover group instance hits 1 bin each. Okay, so bin 1 is hit by instance 1, bin 2 is hit by instance 2, and bin 3 is hit by instance 3. Okay, so when you OR it, it will show it as a 100% functional coverage. Okay, so it will show it as a 100% functional coverage because it is merge across instances. So when you say merge across instances, then what it will do is, if any one of the instances provides the coverage, it is sufficient. Okay, so unique coverage should be provided across all the instances. That is what the merge instance option means. And when the merge instance option is not set, then it resolves to doing the weighted coverage across all the cover groups. And when you do the weighted coverage, then in case of our 3 bins type of an scenario, it will still be stuck at 33% only. Assuming that everybody takes an equal weight, then it will still be stuck at 33% only. Okay, it won't become 100%. But when I do the merge instance, it will become 100%. So we'll look at some real examples as well, but that's the whole idea. Okay, and then for per instance coverage to be reported, then you need to set there is an option called per instance. So you need to set per instance. When you set per instance, then your per instance breakup gets reported. Okay, if you don't set it, it won't get reported. Okay, that's another point you have to keep in mind. But the main core concept that I want you guys to keep in mind is that the way we report at the overall cover group level, okay, is just a view. Okay, so even when I set, like for example, if I change the merge instance option to either 0 or 1, okay, that doesn't change anything in terms of the way it gets reported for an individual instance. Okay, it doesn't change anything. Okay, and if I change the weight at the entire cover group level, the type option also has a option called weight, and then option also, which is per instance level, also has an option called weight. Okay, and if I set it at the type option weight level, it doesn't affect the weights of these individual cover group instances. It doesn't affect that. Okay, it only affects the results that is reported in its aggregated form. Got it, right? This is an important point, that whatever we set at the type option level, it only affects what we report by aggregating. It doesn't affect the individual way the coverage collection works. So that is why I was trying to make a point that you have two different views. One is how it reports at per instance level, and how it reports at the aggregated level. So when we say type option, we are controlling how it reports at an aggregated level. When we using the option, we are controlling the reporting as to how it happens at a per instance of your cover group level. And those two are two different, just the views of it. You collect all the coverage information, and how you report it when you aggregate it is controlled by type options, and how you report it individually is controlled by your option. That is what you need to have the clarity. We look at what are the various options available. So I know some of the doubts might be coming in your mind. Just hold on for a while. we have some examples. So when you look at examples for some of these ideas will become more clearer. So the various options that we can set under type option is the first one is a weight. Okay, so you can set an integral value. So if set cover group at a cover group syntactical level, so it is at the overall cover group as a whole, it specifies the weight of this cover group for computing the overall cumulative coverage of the database, of the saved database. If set for a cover point, okay, or a cross level, then it specifies the weight of cover point or the cross corresponding to whatever the cumulative coverage of the enclosing cover group. The specified weight shall be non-negative integral value. Okay, so the type option, now when we set at cross or the cover point level, it might sound confusing. We are saying the type option is for the entire cover group level, and why are we talking about a cover point and a cross level? So here what you need to understand is whatever the data that I have aggregated across the cover points, across the crosses, to report the across, like as a cover group as a whole, this weight is affecting them, not at the individual instance level. Got it, right? So we take the individual instances level data, but when we aggregate them to a one cross and a one cover point at the overall cover group level, you are specifying the weight. Okay, this type option weight you can specify. Now again you can specify it at the overall cover group level, which gets used when aggregating across cover groups, and then the individual cover point and the cross, when you specify as a type option, it gets used for the aggregated values of the cover point and the cross coverages. Okay, because those aggregated values are required to compute the coverage at the cover group level. So that is this weight, that is how it gets used. And then you have you can set a goal. So what this goal means is that when we will see eventually, so when the coverage information gets presented, then it will show you like whether it is red or green. Okay, so if the goal is met, then it will show as a green, and when the goal is not met, it will show it as a red. So you can specify at what point that how much percentage of coverage, if this particular cover group gets, is sufficient for you. Because sometimes, as we have talked about it, right, like verification is all about prioritization. So I might say a low priority cover group, if it achieves 60% functional coverage, it is sufficient. We'll consider that as done. So I can set the goal number for this particular cover group as 60%, right? And then that guy will be considered as done. So it will show up as a green. Okay, so you can set the goal at what point, at what percentage do you want it to see it as done. So by default it is 100, so it has to hit everything, but you can set it as 60%. So once the 60% is done, that cover group will be considered as done. And comment, you can put a string you can put a string over there which tells what this particular cover group is doing. Like let's say if we take an example of whatever the ports that we are talking about, at type option level I can say this is for all the ports. That's what I can say in the comment. And strobe, so there is an option called strobe, which takes a boolean value 1 or 0. It controls when the variables get sampled within the cover group. So if you want it to happen in the postponed region, then you can set the strobe equal to 1. Okay, so this behaves similar to the strobe system function call. Okay, so you can set it, especially this is useful if you are doing the microarchitecture or the interface level coverage. Then you can set this particular option so that what happens is if I am doing, like let's say because of I am doing like a multiple value changes within a time step for some reason, and you don't want that to be captured, then you can set the strobe equal to 1, so that the coverage only gets the whatever the values that I am sampling only gets sampled towards the end of the time step. And then you have this merge instances option. So as we talked about, if you set this, then it will OR all the coverages across the instances and then report the final functional coverage. But if you set it to 0, then it will just do the weighted average across all the cover groups. So when should you be using it? So let's say that you have a single design, then you are creating a multiple instances of the same module. Then if you simulate one of this particular instance, right, it is sufficient. Okay, if even if your one instance of the design achieves 100% functional coverage, because it's the same design that you have instanced again and again, right? So one of them achieves also, it is sufficient. So in that case, what you do is, you don't want all the instances to be uniquely covered. That is, you don't want 100% for each of the instance, because it's the same module that you are instancing. So what you can do is, you can set the merge instance equal to 1, so that whatever each of the instances is able to gather uniquely, you merge it, and if across all instances I am able to achieve 100%, that is more than sufficient. But if it is all separate, then you want to say, if you want to see that every instance should achieve 100% functional coverage separately, then you set the merged instance equal to 0, then it will go ahead and do the weighted average. This distribute first, I think, is not really relevant for the simulation based verification. It's more geared towards the formal verification. So in the previous slide, we looked at the option for reporting the entire cover group, right? So how does that reporting, can you use the options to control that particular reporting? This one we are now looking at per instance level, how can you control the reporting? Okay, so I hope that point is becoming more clear. So these are, like, you will see that the options will look similar. Okay, because the nature of coverage is similar, right? Either at per instance level, or when you're aggregating it at the group level, the basic fundamental remains same. So you will see that options are also, that is why the options will also look similar, but they apply to different view. So that is what you need to remember. Let's look at it. So we have name, so you can give a name to a particular instance, then you can provide an unique name that gets reported in the coverage report. Again, you can specify the weight. Now when you specify the weight here, this option dot weight, the previous one was type underscore option dot weight, this one is option dot weight. So this now applies only to a particular instance. So we will see when in the examples, when we set the type option, we will typically be using the scope resolution operator, right? Like the name of the type, like you remember the class type, right? So class type, scope resolution operator, and the whatever the type option dot whatever some parameter, right? So that is how we will set. So it is for the entire type, but when we set it per instance, we are creating multiple handles for the instances of CG. So we are going to be per instance name, whatever the instance name of CG dot option dot particular value, or CG instance dot cover point dot option dot whatever the value. So we are now going to be, the way we access it, it will show the difference, that the type options will be accessed through the cover group data type name, whereas the options will be accessed through the CG instance handle, so that we will be able to see. So you can now assign the weight, and this weight will be applicable to only that particular instance of the cover group, which you can apply it at the entire cover group level, or at a cover point level, or at the cross level. Goal again behaves the same way. You can define for this particular instance, when do you say it as 100%. Comment, you put a string. So here now, if I had a multiple ports, for the type option, I would have said across all USB ports. Here I can say port 0, port 1, port 2, so that I know which port I am talking about. Then you have the at least. So this specifies that minimum number of each bins that you would like to see it hit. Okay, so typically what happens, if it is hit once, it's considered as done. But let's say you have an important feature, then what you want to do is, you don't want that to be hit only once and then you call it as done. So you want to say it should be at least hit 10 times. This particular scenario has to happen 10 times. This particular value has to happen 10 times before I can say that this particular the requirement is met. Okay, so you can put at least number, and when you put that particular number to a greater than one value, then it has to hit so many times for it to be marked as done. Okay, so that's what it is. Auto bin max we have already been seeing. So this is only applicable for cover point, not for the cross. So when you don't define any user defined bins, the SystemVerilog will create these bins for you. The default value is 64. So whatever is the variable value, it will take it and divide it into 64 equal range, and if there is additional values left out, it will be included in the last range bin that it creates. Okay, so that is what is the auto bin max. We have looked at few examples as well in the prior. Then you have the cross number print message. So this enables you to control that if the bins that are not hit, should they be reported, because sometimes they can be many, so they have provided that option. Then you have detect overlap. So you are defining either the range bins or the transition bins. So sometimes we have seen in our own examples that we had overlapping values in the two bins, right? So overlapping ranges can be there in the two bins. So if you want that to be reported as a warning, then you can set detect overlap. And then you have per instance option, which is an important one. So if you really care the coverage to be reported for each of the instances, so that you can go and find out if you want to really go and close the coverage for every instance or want to analyze it, then you can set per instance equal to 1. But if you are doing multiple instances of same design and you are happy that overall across all instances if the coverage is met, then you don't care about it, then you can set per instance equal to 0, and at the top type option you set merge instance equal to 1. Then that would be a more meaningful number. At the functional coverage, why these so many options are provided is there's so much of data that gets generated, right? So analyzing everything for a complex project becomes harder, so you want to configure it such that it provides you some meaningful information. So then there is one get instance coverage option. So we will see, so coverage anyway at the it gets dumped in the database, and then eventually you can either look at it in the GUI, or you can generate a HTML report, or you can generate a text report. Along with that, you also have a procedure calls. Okay, so this, like for example, there is a get coverage or a get instance coverage type of functions, built-in functions provided within the cover group. So within each test you can query that and print it. Okay, so sometimes people want to do some fancy automation. Then what you can do is within a test you have saying that these 4 or 5 cover groups needs to be met. Then you can, like, you do one iteration meaning one round of, let's say I generate 100 transactions, then the attached cover groups to those particular tests, I will query them using the get coverage. The coverage criteria is met, well and good. If not, I'll go to one more 100 by tuning some things, right? So if you want to do like, so then the test will automatically run few iteration by itself to achieve the necessary functional coverage, right? So if you want to kind of close in a loop, that you generate the stimulus and then query that within the code. It's not that, it's not a post processing step, so simulation is still running, so you query it and then you can decide to tune something else and rerun the some iteration loop of the test sequence. So if you want to do such things, then you can do the get instance coverage. It's also helpful for quickly checking the functional coverage instead of going through the entire process of report generation and all that. We'll look at an example, so that will give you more idea. We have been saying that the per instance option or even the type options can be applied to like each one of them can be applied to at a cover group level, at cover point level, as well as at the cross level. So now it might slightly be confusing that which one applies to which one, right? So which option applies to which one. So this is the table that summarizes it. It's like, for example, if you take a name, it's applicable at the cover group level, but it's not applicable at the cover point and cross level. Weight, you can set it at all 3 levels as we have looked at it. So when you set it at a cover point and cross level, that gets used for computing at the cover group level, and whatever that you have set it at the cover group level, it's for that particular instance, and it will get used when all those instances are clubbed, and when you want to compute at the overall the type option or the overall cover group level. So this particular weight gets utilized. And then goal, you can set it for all 3 of them, right? At what point do you say it has done? Comment, you can again set it for all 3 of them. At least then you can again set it for all 3 levels. auto bin max, it's only applicable for the actually at the cover point level. You can set it at the cover group instance level, which becomes applicable for all the cover points, or you can set it at an individual cover point level, but it's not applicable for the cross. Of course, cross num print missing, it's applicable at both the cover group level, then it will be default for all the crosses. Otherwise it will be only applied to the cross. So note that this what we are talking about is we are just talking about option. We are not talking about type option. So if you don't, that one concept that I would like to repeatedly clarify, if you set something at type option level, that doesn't propagate down to option. That doesn't happen. Those are two different just views. Okay. Why I'm saying that is, for example, if you see this cross num print missing, I am able to set it at that particular instance level, and that migrates by default to each of the crosses that have been defined. And then for a particular cross, I can again define it at cross level and override it, right? But setting it at that particular instance level migrates to all the crosses. But setting it at the type option level doesn't migrate to all instances. Okay. So detect overlap, yeah, again same concept. You can set it at the cover group level, migrates to all your cover points, and then you can set it at that specific cover point level as well, which can detect the overlap in either the range bins or the transition bins. There's no such concept available for the crosses bins are too complicated. Okay, so per instance level, it's only applicable at the cover group level. It's not applicable for the cover point and the cross level. Get instance coverage, again it's a get instance coverage, so it's applicable only at the cover group instance level as a whole, but not applicable at the cover or cross. Okay, so we have two objectives in this slide. Okay, the first objective is we will establish a base example. Okay, and with this base example, what we will do is we will vary few options and look at it. Okay, so the key option that I really want to play with in the next few slides is this merge instance and the per instance. Those are the important ones. Rest of them, they are important, but they are not confusing. But these two things are important and confusing, so we will make sure that we get clarity over there. But with this we will establish the example, how the example is going to look like, so that in the next time when we vary it, you have an idea that where are we varying it. And then we will look at the distinction in terms of type options and option in terms of real implementation. Okay, so far we have been telling so many things in words, but only when we look at it as a real code and then we correlate it to results is when really it becomes clear in our head. So we will do that. And then how does an overall, once again we will look at the coverage report. So we had looked at it at the beginning of this session. We'll look at it once more just to refresh ourselves how the overall information gets reported. So in this slide we are not going to go too detail into each of the numbers and all that for per instance merge instance, that we will do it subsequently. Here we just want to establish the fact that when I change something at option level, how does it behave, and when I change something at the type option, how does it behave. Okay, so what is our code? So we are defining an enum data type called LTSSM state, and we are defining inactive U1, U2, U0. So these are the states we are defining. We are defining one state variable, and we are defining one int unsigned t. There's one more variable we are defining. What we are going to use, how we are going to use, look at it. We'll look at it. Okay, so we are saying cover group LTSSM, and then we are passing a formal argument. Note that we are passing it with a ref. So that every time I call sample, whatever the change in this particular variable that has taken place, it can be used within the cover group. Of course, I could have used it with the based on the scope as well, just to show some variation. I have used the passing by ref. Okay, so here I am now saying I'm setting the first option. So when I'm saying option per instance equal to 1. Okay, so this is the instance level option. Now the instance level option can be set at two different places. One, I can set it within the cover group declaration. Second, when I instance a particular instance, there also I can set it. So when I set the instance option within the cover group, then those remain applicable by default to all the instances. If I want, I can use a specific instance handle dot option dot a particular value. I can override it as well, so that is possible. Per instance, of course, you set it at the declaration level, but the other options you can change it, right? Per instance doesn't make, you can't say one instance of option it is set and another instance it is not set, so that doesn't make sense. But for the other options you can do that. Okay, so then we are setting the type option. So type option will be for the entire cover group as a whole. So this won't appear within the instances. Okay, so I'm setting type option dot comment. So what we are going to do is we'll set the comment with the type option and also with the option, and we'll see how that plays out. So I'm saying type option dot comment is equal to all USB ports, and I'm saying type option dot merge instance equal to 1. That is, I want it to be ORed together across all the ports because I'm instancing the same design multiple times. So if each of the design is providing some parts of it, if put together is covered, then my original design is anyway completely covered. So I am saying merge instance equal to 1. I'm defining one cover point, and that cover point is based on this variable that I'm passing by ref. And now if you notice, I'm setting one more option dot comment. Okay, so now this option dot comment is a default comment for all the cover points for all instances of this particular CG LTSSM cover group. So I'm set that I'm saying LTSSM state CP. I have one bin per value, and I am just listing all the states that I have defined. Nothing fancy, very simple. I've kept it simple because there is, we are dealing at the complexity at a different, our focus is on a different angle over here. Then what we are doing, we are creating 3 instances of this particular CG LTSSM because we have 3 USB ports in our design, and then I have put one initial begin end block to create some stimulus to apply to this particular cover group. So what I'm doing, I'm saying for int I equal to 0, int I less than 3, I plus plus. I am now instancing for each of these handle of the cover group. I'm instancing the cover group, and while I'm instancing, I'm passing the respective LTSSM variable to that particular cover group, which it takes it by ref, and hence samples it over again and again whenever I call that particular cg.sample. Now comes the interesting part. So what I'm doing is, now for every instance I am changing the option dot comment. Okay, so here I had set the type option dot comment, and here I am setting option dot comment. And what I am saying concatenation of 2 strings. I am saying USB ports, and then I am concatenating with this particular index value that I am looping, so that I can get to see for which particular port. Okay, so that's what I'm doing. And then I am setting per option level goal. Okay, I want to set different goal for different instances. So I'm just saying 60% for the 0th index, because 60 plus I multiplied by 10 I am doing. When I is equal to 0, it will be 60, and when for the port 1 it will be 70, and for the the port 2 it will become 80. Correct. Okay, so we will have 60, 70, 80 respectively. And then after coming out, what I am doing is I am saying USB of port 1 and dot port LTSSM state, which is the my cover point. Okay, and for that particular cover point, what I am saying is I am saying dot option dot comment. Okay, so now I had set the default option per instance option comment to LTSSM state CP. So what will happen is the 0 and the second instance will have this default comment, whereas for the first one I am overriding to saying port 1 LTSSM CP, just to kind of distinguish that can I access it the per instance cover point option. I am doing this, and then I'm just putting this, not very relevant, but just for the completeness I'm quickly going through. So I'm saying repeat 5, and then for each of the LTSSM state variable that I have declared, I'm doing standard randomization of this particular TE variable that I had defined unsigned int, because anyway these enum values gets implemented as unsigned int. I can't do standard dot randomize directly on the enum. Okay, so now you see the benefit of class based randomization. If you relied only on the basic randomization, how hard it is. So you randomize that particular TE with the values of whatever the enum types over here, and then I am saying that particular LTSSM current state of I equal to, I am doing the static typecast from the int to the enum and assigning it to this particular variable, and I'm just doing the dollar display of what got generated, and then I am calling that CG the USB ports of I, which is nothing but the handle that I had created, dot sample. So the corresponding instances sample function I am calling, since you are passing the variable by ref, it will utilize the latest value that I had created. If I had not passed it by ref, then whatever the initial value, only that would have gotten sampled again and again. But since I am passing it through the ref, it will be able to see the latest value, and I am calling sample, and so these are just the various values that get generated when I run through this iteration, and this is how the report will look like. Okay, so in this report we have already seen at the top, if you look at, it will be reported at the overall cover group level. Okay, and at the below we are able to see the reporting for each of the instances. So if you see, now let's correlate this report to what we have set over here. Okay, so let's start off with the comment. So I had set the type option dot comment equal to all USB ports. Okay, now that appears over here because this is the overall cover group type level information that is being reported. So this particular comment comes over here. Now if I look at, for every instance, if I look at the comment that is coming out, I see USB port 0, USB port 1, USB port 2, right? And that is something that I assigned over here. So this is only the per instance level information. Note that it's not showing up anywhere over here. It's only showing up over here at the instance level. Okay, and then I could also control for this instance 1, I could control the comment for the CP, saying it's some port 1 LTSSM CP. So here if I see this particular blue highlighted line, so I am seeing port 1 LTSSM CP. So that particular cover points comment has been updated. Whereas if I look at the instance 0 and the instance 2, it remains set to the default value, which is this LTSSM state CP. It remains set. Let's look at one more information to convince ourselves that how the type option and the option are behaving. So I had set this goal. Okay, so I had set 60, 70, 80 for each of the instances. So if I look at for the instance 0, and if I look at the goal, my goal is 60. Okay, and the current percentage that it has achieved is 75%. Okay, if I had not set this, it would have shown it as red. Like for example, this particular cover point, it is showing it as red because it's not 100%. But since the goal for my entire this particular instance is only 60 and it's already hitting 75%, it is showing full green because it's done. That's what I really care for, right? So only 60% is sufficient. Since it is already 70%, it is happy. Then here we have set 70. I think here it has become 75, and it is able to say that it is fully done. But what you need to note is that I am able to see this 60 for the instance 0, 70 for the instance 1, and 80 for the instance 2, and depending on their current coverage percentage and the goal, they are marking this green. And one last thing we will just quickly look at, see, although we have certain gaps over here at the individual level, but since we have done the merge instance at the instance level, it is showing it as full. Okay, so this point anyway we will go deeper into next few examples. So I hope this now gives you the clarity of how the type option versus the option works. We will contrast how the merge instance and the per instance behaves. So there are, since we have these two variables, there will be 4 combinations. So let's look at each of the combinations. So if I say type option and merge instance equal to 0 and then per instance equal to 0, so both of them are set to 0, then the weighted coverage gets reported across all instances. And since I have set the per instance equal to 0, no per instance coverage gets reported. So the report for the previous example would just look like this. So there's no per instance level breakup I can see, and it has done the weighted average across all the instances, and then this is the report we see, and we see that all USB ports, which is what we had set it at the type option level. Now if I set type option equal to merge instance equal to 1, and if I continue to set options per instance equal to 0, then the logical OR of all the coverage across all the instance gets reported, but still no per instance level coverage would be reported. Okay, so since we have done the weighted average, if there were any gaps, those will still show up, right? But if I not done at a merge instance level, there is a higher probability. Okay, in this particular example we are seeing 100%. Doesn't mean every time we will see 100%, but since it's a logical OR, it will reach quicker. It will reach 100% quicker because any instance contributes some unique thing. It all gets adds up. So here you will still see at the overall type level, instance level breakup is still not available. So we have set here merge instance is equal to 0 and then the per instance equal to 1. So we calculate the weighted average of the coverage across the for the type at the type level, at the overall cover group type level. So here you can see that overall coverage at the entire type level as well as per instance level gets reported. Since we have set per instance equal to 1, for each of the type it gets reported, and then the overall cover group type level also gets reported. And since we have set the merge instance equal to 0, it's doing the weighted average of all three instances. So you can see that like this instance is about 75, second is at 75, third is about 100. So it does the weighted average. So we are anyway, we are not mucking with weight, so all the weights being equal, so you get somewhere around 83%, right? So that's what you see when you do the merge instance equal to 0. So you get the breakup, but you get the weighted average. Okay, so here we are doing merge instance equal to 1 and options per instance equal to 1. So here what happens is, although we have is the same results, right? So you see that per instance level result has not changed. Okay, just I have set this to now merge instance equal to 1, and then the report, the view at the overall type level has changed. So now it has become 100% because it is able to find the unique coverage, right? Like for example, this instance itself is 100%. So if any one instance is 100%, your overall type becomes 100% because it's a logical OR of all the instances. So there are certain built-in coverage methods that the cover group provides that can be utilized. So we have already looked at sample, right? It triggers the sampling and it can be overridden and you can pass the parameters to it. So we are just interested to look at some of these get coverage methods, and rest of them they are there. You can go through them, and the usage is pretty low. So this is the only one, as like if you want to do any automation or something like that, this still will be useful. And I am also looking at it from the point of view of just reinforcing some of the concepts as a part of this example. So one is that at the end in your test, if you want to display the coverage for a particular cover group, you can do this way. So display cover group, you can put a name, whatever your name, and then it returns the real number. So you put %f, and cg.getCoverage will tell you the overall coverage a particular cover group has achieved, and that is something that you can that you can print it at the end of the test. I think like even if you play around the coverage in EDA playground, you can do this to get a quick sense. Of course, you can set up the files to get the final coverage report as well, but this also is useful if you are playing on the EDA playground. But let's look at an example. So we have a cover group CG, and we are passing a few arguments over here. Note that this is the point that we had discussed, so I just thought that this example would be interesting. It's not just from this methods point of view that I'm interested to demonstrate, but overall cover group concepts point of view as well. This example is important. So we are passing this xb and yb pass by value, whereas whatever we are sampling in the cover point, we are passing by reference. So that is one concept that it shows. Then we are using cover point x and y, whatever we have passed by reference, we are sampling it over here, and then we are defining the bins, and then bin per value, and then the bin range we are controlling by using the parameter that we have passed as a input pass by value, right? So we are using 0 colon xb and 0 colon yb for the y, and these values when you pass it have to be constant values, because when the new gets created, it has to expand. All right, so as we have discussed, so we create two instances of this particular CG, CV1 and CV2 new, and we are passing some different variables. So 1 2 ABCD and then 3 6 CD. Okay, so we have done that. Now is when we need to pay attention. So let's say now I say CV1, which is for this particular instance dot X, this particular cover point. I say get instance coverage, and I can pass these two arguments, and then along with returning that real value, it also returns me the count of bins. So sometimes percentages can be misleading, so you want to really look at the actual count that has been hit and the total number of bins that are present. So here it will say total equal to 2, because we are passing for the CV1 we are passing the value of XB as 1, and then 0 to 1 it will become 2 bins. Similarly, CV1, when I say get instance coverage, I am getting the total value as 5. That's because my XB is 1, so it will become 0 to 1, 2 bins, and then my YB is 2, so it will become 0 to 2, which will become 3 bins. So total we have gotten 5 bins, right? And then here now, if you see now, these were 2 at the instance level, right? So now I'm looking overall at the cover group level. So I'm saying cover group level, entire cover group level, say X and get instance. So I'm using the scope resolution operator because I'm operating at the entire as a whole as a type. All right. So cover group can be operated whole as a type or at the particular instance level. So cover group as a whole, when I say X and I say get coverage, this count becomes 6. So why it becomes 6? So if you see over here, for the CV1 we are passing value of 1, so it is 0 and 1 2, and then for the CV2 we are passing the value of 3, which is 0 to 3, which will become 4. So those 2 plus 4 becomes the total of 6 bins. Okay, and then if I do CG get coverage, okay, so now it will be sum of all the bins. Okay, so this 1 will become 2, right, and then 2 plus this will be 3, right, so it will become 5, 5 plus 4 9, and 9 plus 7 16. Okay, so we will be able to see 16 bins. Really what I wanted to show you guys is how the bins get created. One more a quick refresher, because often when you look at it again from different point of view, the points become clear, because with one example some point would have become clear, with another example some other point becomes clear. So with this we were able to see that how the bins get created and how we can access it at that type level versus the instance level. That concept, I think it demonstrates it very beautifully. So yeah, this concludes, I think this is the last part. So this concludes the coverage session. Okay, this concludes the functional coverage part. So we started off from contrasting the cover group to the assertion based coverage, right? And then for all the class based word, the coverage, functional coverage is typically implemented through the cover group. That doesn't mean that you cannot use cover group construct for implementing the microarchitecture type of a or the interface level functional coverage, but the assertion or the property based functional coverage is more well suited over there. Then after that we looked at the how the overall the coverage model implementation process looks like when you use the cover group construct. It's a 3-step process. The first step, you do the coverage declaration. Second step, you declare the handle, and then create an object or create a cover group, construct the cover group using the new, and then you call the sampling function either through an implicit or an explicit sampling method. Then we looked at various components of the cover group in detail. So we know that cover group, you can pass the different arguments to it, and those arguments can be used for option, for defining bins, or for the sampling the values within your cover point. So you can use it for them. And then we saw that if you are using it for sampling the cover point, that it needs to be passed by reference. And we also looked at that the passing information to the cover group can be done in multiple ways. You can pass it by ref, or you can pass it by value by overloading the sample function, or the cover group can look at what is visible within its scope, whether the properties of a class or the variables declared within the module. It can look at it and it can use that for sampling. And we saw the implicit by using an event, and then explicit sampling by calling the dot sample method of the cover group. And then we looked at the the major components of the cover group internally. We have the options, and how we could see that we have at the type level option and we have the instance level option, and how do they behave differently to create different views of the coverage that gets reported. How do they control the behavior of the cover group? We looked at it and we contrasted them to and make sure that we have understood. I think among them there are multiple of them. The key ones are at the of course those name comment they get used, but the key ones that you really need to sort of remember, like the auto bin max is one of the important one, and the most important one is the per instance and the merge instance. That's the most key concept with respect to options. Okay, rest of them are simple, and some of them don't even really get used. But the merge instance and the per instance, it's really an important option. That's why we contrasted it from the various angles. Then we looked at cover point, how a cover point represents the bins for a given particular variable or a single variable or a single expression, and how it's implemented in the form of counters. If we had to implement it without the cover group construct, we kind of looked at the idea and understood it. And then we went deeper into how do you define different types of bins for a particular cover point, like how do you define the legal bins, how do you define ignore bins so that you can eliminate them, and then how do you define illegal bins. We looked at those ideas, and then like bin per value, and then for the group of values a single bin, that concept we looked at and we understood. And then we went to cross, which you build on the top of cover point, and then we understood how the bins of cross are different from the cover point bins. That's an important point. I hope that you were able to get that distinction. And then in the cross, when the bins explode, how do we use those different functions, the bins of and intersect for selecting certain cross bin tuples, and then for width, so that you can trim the bins that you have selected using the bins of and intersect. And then you can use the matches to control the number of matches that you need to have in order to for it to be included. So we looked at the usage of all those operators. And then we have overall looked at how the various coverage reports look like, and how they get reported at the overall type level and at the per instance level breakup, and how the calculation is done in order to report it at the different level. So we have looked at it and we have understood those concepts. So at this point, I think this one we conclude the cover group construct. Thank you for listening.